Hello Stat 200, welcome to Lesson 7. This week you'll be learning about common distributions. The normal distribution and the binomial distribution are the two that we're going to cover this week. In terms of your reading in the Lock 5 textbook, I recommend working through them in this order. Section P.5, Chapter 5, and finally Section P.4. This matches the order that the content is introduced in the online notes and also the order of the questions in your Wiley Plus homework. These are the key topics that we're going to cover this week. This lesson is really a bridge between the simulation-based inference that you've been working with, in other words, bootstrapping and randomization procedures, and the more traditional methods that we're going to be focusing on for the rest of the semester. Let's start with a review of the normal distribution. You were first introduced to the normal distribution in Lesson 2. This shape should look familiar. In the last 3 lessons, you've been constructing bootstrap and randomization distributions, and many of them were this shape. Here we have a few examples. This is a bootstrap distribution for the difference in 2 proportions. Here we have a randomization distribution for a correlation, and a bootstrap distribution for a single mean. Note that these are all approximately normally distributed. The example that we have here is a special case of the normal distribution. This has a mean of 0 and a standard deviation of 1. This is our standard normal distribution, also known as the z distribution. The notation at the bottom here tells us that we have a normal distribution with a mean of 0 and a standard deviation of 1. You will compute test statistics in this lesson, and this is the z distribution that you'll use to find the p-value associated with those test statistics. In this lesson, you'll also see how this distribution can be used in constructing confidence intervals. We can use the normal distribution to approximate sampling distributions in many cases when the sampling distribution is approximately normal. This brings us to the central limit theorem. This states that if the sample size is sufficiently large, the sampling distributions for many commonly tested parameters will be approximately normally distributed. So far, we've used inferential procedures for one sample mean, one sample proportion, the difference in 2 means, difference in 2 proportions, slope of a simple linear regression model, and Pearson's R correlation. For all of these, the sampling distribution will be approximately normal if the sample size is sufficiently large. In terms of what is meant by sufficiently large, we'll learn more about this over the next few weeks. Essentially, it's determined by the point at which the sampling distribution becomes approximately normal. For this lesson, we'll still be constructing sampling distributions in StatKey, so we'll be visually judging whether or not our sampling distributions are approximately normal. In practice, when we're conducting a hypothesis test or constructing a confidence interval, we often use the normal distribution or other distributions that you'll see in the next few weeks, as opposed to bootstrapping or randomization procedures. In situations where the sampling distribution is approximately normal, we can use the normal distribution to find the p-value for a hypothesis test, or to find the multiplier that we need to construct a confidence interval at any confidence level. Most of this week you'll be focusing on the normal distribution, but in section P.4 and in the last section of the online notes, you'll be introduced to binomial probabilities. A binomial random variable counts how often a particular event occurs in a fixed number of tries or trials. In order to be classified as a binomial random variable, the following 3 conditions must be met. There must be a fixed number of trials, in other words, a fixed sample size. The probability of success is the same on each trial. In other words, the value of p, or the probability of a success, stays the same. And finally, the trials must be independent of one another. So the result of one trial cannot have any impact on the result of any other trials. If these 3 conditions are met, then we can construct a binomial distribution plot. While the textbook and online notes give you the formulas for computing binomial probabilities, I strongly encourage you to use Minitab Express. It is much more efficient than the hand calculations, especially when you're trying to find the probability for a range of values. We will apply what you learned this week in the remaining lessons as we focus on some of the more common statistical procedures that rely on these common distributions. As always, if you have any questions as you're working through any of the materials this week, please post them to the Lesson 7 discussion board on Canvas.